Okay, let's get working on this now. Today is 6/19. This is video 136. And the topic is what they call in the Regents books special cases, as you can see over here. But what they really mean is how do you handle perfect squares in this math? That is, how do you factor perfect squares? Now, the truth is, the real truth is that we've done this before. However, I deliberately did it before we knew what factoring meant, really, because this is always such a confusing subject for your average freshman. So I'm going to take my time here, re-explain the perfect square trinomials again, what a perfect square is, and then use our new method, that is grouping, to factor these, and then talk about things that come up that confuse kids. So anyway, let's go back to what we did a while back. Right here where I'm pointing, this is just a square. We call it a perfect square, since a square by definition, some number plus 1, with restrictions included. Probably -1 wouldn't be a good idea, right? But some number plus 1, and when I multiply this times this, as you well know, you get what we call a perfect square trinomial. Well, let's go over the properties of a perfect square trinomial. The first term has a coefficient of 1. You're supposed to know about that. But let's be clear. 1 is a perfect square. 1 times 1 is 1. Square root of 1 is 1. It's a perfect square. So it's this. And then the last term is a perfect square. When this happens, and the square root of the first term and the last term add up to double, then you have a perfect square trinomial. Okay? So this times this equals this. You can FOIL it and double check me. And we call it, like I mentioned over here, a perfect square trinomial. Now going on to the second one, 4 is a perfect square, and 9 is a perfect square. The square root of 4 is 2. The square root of 9 is 3. 2 times 3 times 2 is 12. So this is a perfect square trinomial. All I've done is imagine a square and found the area by calling it this. Last case over here that I wrote out, 9 is a perfect square and 25 is a perfect square. Okay? Square root of 9 is 3. Square root of 25 is 5. 3 times 5 is 15. Double that, -20. Oh, that's right, the -30 there. That makes sense, because the second term here, see it, is negative as well. So a negative plus a negative is a negative, and there we go. Here below, that I wrote out before, is the way the math textbooks describe it, because A and B are any kind of unlike terms. And when I multiply them together, I get the format that you're supposed to know, a squared plus 2ab plus b squared. Well, again, let's just review some ideas here that kids find confusing. Remember that the square root of a squared equals a, and the square root of b squared equals b. Kids always find that confusing. So that explains what's going on here. For example, in the last case, 3 is the square root of 9. 5 is the square root of 25. So when I took that, I doubled it, and since the middle terms were negative, it came out to -15 plus -15. Here's the case that pertains to this exactly down here, where the same thing occurs. So here, again, this would be just 3x minus 5 squared that would fit this format, and this one here would be 2x plus 3 squared, which would fit this format. Okay? So these are called perfect square trinomials, and the Regents certainly wants you to know about them. They're obsessed with it, to be honest. And what we need to do now is to show first that the grouping method that we learned is going to work with these. So I'll factor all 3 of these using the method that we know already. But we'll learn that because perfect squares and the problems they give you tend to have larger coefficients. You have to be on guard for that. You have to be watching that. So it's very important at your age to know your perfect squares. I just can't emphasize it enough. You have to recognize the simple ones. And I talked about that all the way back in October when we learned the theorem of Pythagoras, that this will not go away, and they want you to know your perfect squares. So this is the first two cases, if you like, of special cases. And in the next lecture, I'll talk about the next one. So let's just see if our method works, because say you didn't notice that. If you notice what I just pointed out to you, perfect square, and that's all you'll see on the page in the book that I'll give you as assignments and whatnot. They're just dealing with perfect squares. If one of them wasn't a perfect square, it's probably not factorable. Certainly nothing that I have to do here. So this is really special cases talking about the math of perfect square trinomials, and as we'll see, perfect square binomials. Okay, so let's factor this using the method that we know. 1 times 1 is 1. And what two numbers add up to 2 that multiply out to 1? Well, it's pretty obvious. It's 1 plus 1. So we write x squared plus x plus 1. So you should keep that in mind. When it's a perfect square trinomial, you just take the middle term and you cut it in half, because you're just doing the inverse of this operation down here. Keep that in mind, okay? And let me bring this over here. Sorry about that, okay? So there's the 1, the square roots. I'm doubling them. I cut them in half. And now over here, I'm factoring. Factoring again. And this is a peculiarity of the perfect square trinomials. X plus 1 comes up 3 times. But it's the same idea. X plus 1 is attached to this twice. And so there we go. X plus 1 times x plus 1 equals x plus 1 squared, which again just goes back and equals that. Okay? So that shows you if the numbers are small and you don't see it, you'll get the same answer if you do grouping. So I'm going to erase this and show that it works for the bigger ones, the bigger coefficients. However, it's best to use your properties of perfect squares, because I'll mention this in passing. They're never going to ask you, if it's not perfect squares, to do big coefficients. There's no purpose in that. So when you see the big number in the front and the big number in the back, that is the big number on the first term and the big number on the last term. They're almost always perfect squares. Otherwise, they wouldn't ask you. Okay? So I'm going to do this one here. And here we go again. 4 times 9 is 36, and 6 times 6 is 36, and 6 plus 6 is 12x. You should see that, okay? So we just break it up. Okay, once you see that, you're good. In the last case, it's going to be a little tougher because, like I said, since we're working with perfect squares, sometimes the coefficients get much bigger, and got to worry about that. So we rewrote this, and there's our 2x, which is the GCF, and there's x, let's see, what do we have here? 2x, whoops, there's the 2x again, and there's the 3, and then we write it out again, 2x plus 3, and what number makes that work? Plus 3, and there you can see it all over again. 2x plus 3 squared. Okay? So this is just showing you that the method that I taught you before always works. It doesn't matter, as long as it's factorable, of course. But here in this last case, this third square that we talked about, it gets a little trickier because if I follow the method that you've been taught, 9 times 25, if I go over that, that's 225. And so you'd be looking at something like this. What two numbers add up to, multiply out to 225, and at the same time add up to negative 30? Now, if you didn't have perfect squares in your mind, you've got work in front of you. But a perfect square times a perfect square is always a perfect square. and we're subtracting here. So half of negative 30 equals negative 15, and you're set. So it's negative 15 times negative 15 equals 225. But most kids don't bother with all that. I'm just making it make sense. And the proper way to do this, or the easier way to do this, is 3 times 5 times 2. So whatever you're thinking, I'm marking it out now, cutting it right down the middle term. It's bound to work because after all, a perfect square is just a number multiplied by itself. That's what it means. Perfect squares multiplied by themselves end up being perfect squares, but we won't get into that right now. And there's factor, there's 3, looks like that's the number that works. And it's a minus this time, so there's 3x minus 5. And when I write this out again, we can see that the math is working the way we want it to work. And there you go, factoring both ways, and there we go. Okay? So that's the basic idea behind these. I'll give you some exercises, and I'm going to save for the next video a discussion of 2 terms, perfect squares with 2 terms, because that needs its own application. So I'll give you some problems to do maybe over the weekend, and these are the easier ones. And notice again, I'm repeating myself. If I look at the third one, you should be suspicious right away at the size of the coefficient in front of the x squared and the last term. They'll never give you the bigger numbers because it's too much work unless they're perfect squares. And so here one more time, 3, 5, middle term, 3 times 5 is 15, half of 30 is negative 15, and you don't even need to use the method, however, that always works. So I'll leave it here where I felt it was important to explain what I'm talking about, and they'll certainly ask you to factor perfect square trinomials. And in fact, in the math where we're heading, it will be very important just to basically recognize them to avoid this kind of stuff. Okay, so let me post this and then we'll talk more.